I want to start with a historical remark, which is that I was a problem student in graduate school, and the reason was that Bill Goldman gave me a copy of a paper by Dennis called Conformal Dynamical Systems. And I started reading this and I thought, this is the right stuff. It has complex analysis, and it was written with this sort of informal elan. And so when I went to talk to the graduate ombudsman, who was Phil Griffiths, and he asked me what I was going to work on, I said conformal dynamics. And he sort of glowered at me, does anybody do conformal dynamics here at Harvard? And the answer was no. And so I was really a sort of a misfit. And Dennis very graciously took me on as a student in my last year. And, well, I've been his student for the 16 years since then. And like most of his students, it takes a while to appreciate all of the things that you learn from him. For example, one thing I learned, one of his sayings about mathematical research was, every argument proves something. This is good to keep in mind when your proof is not working, because it's proving something. It's just... and another one was, you can't learn with your mouth open. And I still haven't fully appreciated that one. Another one was the beauty of finding the right formulation, not just of the statement of a result, but of the question that the result addressed. So let me tell you the question I want to address today, which is what is the... Just a second. Crumbly chalk. What is the simplest, interesting dynamical system? Okay, so to make this a little bit more precise, I'd like to think of a dynamical systems as being given by formulas. That's what it would mean to give them very simply. So they might have something to do with algebra, and if they're given by algebraic formulas, then they often can be considered over both the real numbers and the complex numbers, and if you're lucky, they give a dynamical system on an algebraic variety. And so to make this more precise, instead of saying dynamical system, let me say here automorphism. Automorphism of a complex manifold. Let's say a compact complex manifold. Because I'm still seduced by the power of holomorphy. I'd like to I'd like to use those methods to try to address dynamics. And so with the idea that this kind of example might have something to do with algebraic geometry, let me describe for you a very simple dynamical system. So suppose you take a pair of ellipses in the plane, a pair of conics, C and D, and you pick a point on the outer conic. Then you can draw a line through that point tangent to the inner conic, and then another line and another line. You get a sort of billiards-like picture if you keep doing this, and it goes around, and it might be that after doing this enough times, you come back exactly to where you started. Okay, so actually there's a theorem about this due to Poncilla, classical theorem of algebraic geometry, that says, well, this is a way of constructing a sort of polygon, and it says that the polygon closes for 1p if and only if it closes for all p. So this dynamical system has the same qualitative behavior independent of the point p that you started with. So I want to start the talk by proving this theorem. And saying something about this dynamical system. So how could you prove this theorem? Well, the first thing is to define the dynamics. The dynamics should be a map of a space to itself. So the map, you might think, is the map that takes P on the outer conic to this new point, f of P. Now, what's wrong with that? and F inverse of P.
F inverse of P, there's no F.
What's F inverse of P? This point P here?
No, the other point.
Yeah, this point here, right. Oh, I see, F inverse of P because it's cycled, right. So the problem is that this map is really 1 to 2. If you're given a point on the outer conic, there's 2 choices of points that are tangent to the inner conic. The lie on line's tangent to the inner conic. So to resolve that ambiguity, we should replace the phase space of the dynamical system, sort of an analogy with what Hamill did in his talk, to remove that indeterminacy. So instead of considering the outer conic as the domain of our dynamical system, we could consider the domain to be the set of pairs, say P and Q, where P is I guess the outer conic is D, Q is in C, and the line through Q tangent to C contains the point P. So it's the set of pairs consisting of P and then Q. Q is the choice of one of the 2 lines through P, recorded by the place where that line is tangent to C. And then our dynamical system assumes a very simple form. You see, every point is incident to 2 lines, and every line is incident to 2 points. So there's a pair of involutions on this space E. There's a pair of degree 2 maps, let me call them I and J, map E to itself. And the way you can picture these maps is the following. The locus E in the product of D and C is something that, as I said, for every point on D you get 2 points on C and vice versa. So it's some sort of curve that meets every horizontal line and every vertical line in 2 points. And so there's a natural involution, which is to switch a point to another point on the same vertical line. That amounts to, say, taking the pair P and Q and replacing P by P prime, this point down here. And then we want to change the line, so we change Q to Q prime, which is the other inner point compatible with this outer point. And then we proceed. We replace P by P double prime, and so on. So in terms of this picture in the product of C and D, here's the dynamical system. You just go up and then over, and then up and then over, and down and over, down and over, up and over, like that. That's the whole dynamics. It's just the product of these 2 involutions. F is equal to I composed with J. Okay, so let me just show you a picture of this theorem a little more accurately. So here's an example of a pair of conics where the dynamics really does close. And here's an example of one of these curves E I've just mentioned. So this is a curve in the plane that meets every vertical and horizontal line in 2 points. And the dynamics is, again, you go across and then down, across and then down, and so on. And I've drawn a trajectory of a length about 100 or so. In this example, the trajectory is not closing. So it's filling out this sort of bow tie looking figure. It would eventually be dense. Okay. So now let me turn to the proof of Poncilla's theorem. So what kind of a curve is E, do you think? E is, after all, an object of algebraic geometry. It's defined by polynomial equations. It's one-dimensional. It has a map defined on it to itself, our dynamical system F. Well, it turns out that E is a Riemann surface of genus 2. It's an algebraic curve of genus 1, I mean. It's an elliptic curve. So E is a Riemann surface, defines a Riemann surface of genus 1. And of course, what I've drawn in this picture is just the real points of E. But over the complex numbers, the algebraic equations defining E determine a torus which is isomorphic to the complex plane modulo a lattice. And the genus of a surface is telling you about the presence of holomorphic 1 forms on the surface. So there's a natural 1 form, omega, that lives on this surface. And in terms of the uniformization of the surface, this 1 form is just the form dz on the complex plane, which is translation invariant, and so descends to something which lives on the curve, and this is nowhere equal to 0. Now, what does that one form give us on the real points of this elliptic curve? Well, this one form, which is more or less unique, it's unique up to scale, is something you can integrate over one-dimensional objects. So you can integrate this one form along the curve, and you have a way to measure distances between points on E. So this one form, omega, determines, let me write this, one form, which is more or less canonical, determines a metric on this one-dimensional space, which is isomorphic to just the circle, and everything is so natural that this automorphism must preserve this metric.
So where did this form come from?
Well, it came from the fact that this is a Riemann surface of genus 1. So I could write it down explicitly in terms of the algebraic equations, but abstractly it's present because the genus is 1. Yeah?
Is the fact that when you get to the end of the circle, it looks like suddenly those 2 points come to 1, is that an illusion from the fact that you're just looking at the real part, or is there something special?
When you get to the end of the circle,
Well, you know, the circle you drew, where you bounced it back and forth, looks like you've always got 2 choices, but that's not quite true at the end point.
oh, at the end points, right. So, yeah, so let's see. Right, so here everything looks fine, but if we, right, this corresponds to places where there's only one tangent direction. And you see, these elliptic curves, these conics rather, if I were to draw, in the complex world, they meet in a pair of, they actually meet in 4 points in the complex world because they're 2-degree two curves in the plane. So there are places where there's multi-valuedness, but you don't see it in the real locus that I've drawn here. In any case, the dynamics is still defined at these points. They would just be fixed points of one of the involutions. Okay, so the fact that this is genus 1 means there's a natural 1 form, and we're on a one-dimensional real space, so that gives a metric here. This metric is preserved by f, and therefore f is an isometry of a circle, of a Riemannian circle, and so of course it's just a rotation geometrically. So f is a rotation that is an isometry in the omega metric. And now Poncilla's theorem is clear. You see, if you have a rotation of a circle and the nth iterate fixes the point, then the nth iterate is the identity. A rotation that fixes a point is the identity. And so that's the proof of Poncilla's theorem. This map is actually inducing an isometry of the outer conic with respect to a certain metric that can be defined using algebra. Okay, so what's the upshot apropos my question? The upshot is this dynamical system is not interesting. And in fact, the conclusion is that there are no interesting examples in dimension 1. Dimension n is 1. Right, no interesting examples of automorphisms of compact complex manifolds. So in fact, complex manifolds of dimension 1 are classified by their genus. For genus 0, they're isomorphic to the projective line, P1, and the automorphisms are essentially linear. They come from Mobius transformations. And for G equals 1, we get elliptic curves like the example we just looked at, and the automorphisms are again essentially linear. That is, they come from linear maps on the universal cover, C. Or they preserve this natural 1 form. They're isometries. And for genus greater than or equal to 1, greater than or equal to 2, then the automorphism group is finite. And therefore it's uninteresting. So the upshot is that to answer this question, we have to go to at least complex dimension 2. And here? I don't consider that to be interesting. I mean, in the sense that it can be completely analyzed. The nth iterate of the map can be written down explicitly. So I'll show you some really interesting examples shortly, but I don't, yeah.
So So, but I mean, in your discussion, it was an isometry.
Yeah.
Any
Yes, that's true. That's true. Okay, so let's ask what happens in dimension 2. That's the next candidate example. And in dimension 2, the story actually is almost the same. There's a classification of compact complex surfaces, and it follows in many ways the classification of Riemann surfaces. You can have a surface like the projective plane, or maybe a product of two projective lines, and so on. These so-called rational surfaces. And again, here the dynamics is essentially linear. This is like the genus 0 case. And then there's surfaces of general type, which are somewhat like hyperbolic Riemann surfaces. In any case, these are surfaces whose automorphism group is finite. And then there are various sort of skew products of things. But the main generalization of this case of genus 1 is something like taking C2 modulo a lattice. And again, the automorphisms of this torus are essentially linear. That is, they come from linear maps on C2. And so we've yet to see anything substantially richer than what we saw in dimension 1, except there's a special type of surface that has no analog in dimension 1, and that's what's called a K3 surface. And so the theorem I want to defend is that the first interesting examples, the first interesting dynamical systems are automorphisms of these K3 surfaces. Pardon me? An automorphism is invertible.
Yeah, but in the statement you didn't write automorphism.
What? Oh, the first interesting invertible dynamical systems, yeah. Okay. Thank you. Right, so those of you who went to John Hubbard's first talk may be wondering, what about z squared plus c? And this is not invertible. And those of you who went to his second talk may be wondering, what about the Heynon mapping? And this does not live on a compact complex manifold. It lives on C2. And you saw the kind of histrionics that are necessary to get it to work on a compact space. So by going to K3 surfaces, we arrive at a situation where the dynamical system at the outset compact. And so it may be simpler, in fact, than the Heynon mapping, although the Heynon mapping is easier to write down. Okay, so I should say that these surfaces, automorphisms, are beginning to be studied, and there's a theorem of Cantat that makes this quite precise, which says, makes this statement more precise, which says that that surface automorphisms of positive entropy arise only on K3 surfaces and Riquet surfaces, which are double covered by K3, so they can be reduced to that case. On complex, you have a Nosov mappings, but they're essentially linear. And to be some sort of degenerations of K3 surfaces. Okay, so that's right. That's right. So this is there, and of these, I mean, as I say, these are linear, so they're not interesting in basically one type of surface. So statement. This is one way to try to defend the notion that these dynamical systems, because of the fact that positive entropy, maps on these tori also have positive entropy, but they show you that these are interesting. Okay. So let's see. generalization to make examples, which I major, did in the number, is you take sitting inside of a product. You take a surface. Has several degrees. The degree so I require depthwise lines. And then on this you draw
still is true that with this whole probability, so you pick some, what? It's true even in that using change. What?
If they change, yeah.
Yeah. So I think that one of these KT surfaces with, of course, non-real coefficients. So very a complex, and I think that's a couple of parameters.
Right.
You'll have a 6 point. You'll have periodic. They will have the ability to do some algebra that's going to link the eigenvalues to like transformation.
There is in fact. So remember that the eigenvalues have to be, so the question was, how could this theorem possibly be true? You just take the K3 surface and you wiggle it a little bit, and then the multipliers of the periodic cycles will move, and they'll pass through diagonal values and give zero lists. So that would give algebraic examples that have zero lists. But you take it up.
Why is that statement something not true?
What?
I don't understand why is that the statement something not true?
That contradicts this.
Well,
No, that there are no examples on projective surfaces. Why can't we just take a surface, vary the equations for it, and get the generic derivatives, and then that will give you exactly. Yeah, be diagonal. Okay, so let me point out that the condition, the diagonal condition that's needed is that lambda 1, lambda 2, and lambda 1 times lambda 2. These need to all be diagonal. This is, roughly speaking, what the joint diagonal condition is. Okay? It's actually a little bit more, it's more than this, but it certainly implies this. So we would need to have at least these 3 numbers diagonal. Now this number is nothing more than the Jacobian determinant of the derivative of the bound. Okay? At the fixed point. Now this determinant in the real examples is 1. So in the real examples, in the projected cases, it's always a root of unity. And so as you vary the dynamical system, these 2 values vary, but the product stays fixed. And the reason it's a root of unity is because this is equal to the eigenvalue of f on H02. Because it's the same thing, or H20. It's the same thing as the action of f. This product, this determinant, is the same thing as f star eta over eta. You have this globally defined holomorphic 2 form. The multiplier by which it moves is, in fact, the derivative of every fixed point. So that's already a surprising thing. The Jacobians of all fixed points are the same. And in fact, they're all roots of unity in the projected case. So that's where this unseen obstruction is hiding. That it's equal to this everywhere, right? But it's because of the fact that well, one has to look in more detail at how the pod structure breaks up and what the signature is. But what finds that f star restricted to H20 is preserving a positive definite form in the rejected case. And so it turns out to be an irrational. It's an integral matrix, a unitary integral matrix, so that's why I